Whenever a fingertip comes in contact with a surface, it leaves behind a residue of sweat called latent fingerprint. This residue is enriched in a host of chemicals. Some of them are organic in nature, others are inorganic in nature besides water. Amino acids and proteins are an important group of chemicals in the sweat residue. There are several methods to fix them for the purpose of developing latent fingerprints. Of course, the most common method is the ninhydrin method. The advantage of amino acids and proteins is that they do not migrate within the capillaries of the substrate. So it's most useful to tag them when latent fingerprints are to be developed on a porous item like paper, cardboard or wood. As I said, ninhydrin is the most popular and the most common method. DFO method is a substitute for it. DFO reagent also reacts with the amino acid and protein content of latent fingerprint residue and gives pale purple colored fingerprints. The color of course is pale, not very bright, not very sharp, but the chemical compound formed as a result of the interaction of DFO with amino acids and proteins is fluorogenic in nature. This means that if we impinge ultraviolet light on it or even visible component of radiation on it, it begins to shine. Practically, and in most of the forensic science laboratories, the radiation of having wavelength of about 500 nm is radiated upon the developed print and it shows bright fluorescence. It is so clear that one can observe it even with a naked eye. So as I said, DFO is a substitute for ninhydrin, but it has got several advantages. The prints developed with ninhydrin reagent are not fluorogenic. You can make them to fluorescence by a post-treatment method, and that is that you treat them with a solution of zinc chloride, then take them to a very low temperature of almost minus 200 degrees Celsius and finally observe them under laser. In these conditions, they will show fluorescence, they will become more clear, they will become more sharp. But this is a tedious procedure. On the other hand, the post-treatment required with DFO developed print is simple. One step, you need only a torch, a light source. It can be carried out even at room temperature. The sharpness is comparable to that of the fingerprints developed with ninhydrin. But this is more cost effective, this is more simple, and practically it has been observed that DFO develops 3 times more latent fingerprints as compared to ninhydrin. Another advantage of this method is that even if the ninhydrin method fails, the DFO method can still be tried out as a last resort. Moreover, the method is cost effective, it's simple, it doesn't require a trained hand. Even an amateurish person can develop latent fingerprints on a host of porous items, craft paper, thermal paper, photostat paper, on cardboards and on furniture items. Sooner or later, this will become an important substitute for the ninhydrin technique, which is commonly used.
Dear students, after studying this module, you shall be able to know the significance of DFO reagent for detecting latent fingerprints, the mechanism of reaction between DFO reagent and sweat constituent, and will come to understand the merits and demerits of DFO method vis-a-vis the ninhydrin method. So let us start with a brief introduction of DFO. Fingerprints are still one of the most important contact traces left during the commission of a crime, as their uniqueness puts an individual at the scene. Therefore, it is vital that fingerprint recovery bureaus have methods that are effective in the recovery of latent fingerprints. To this end, a variety of chemical reagents and associated methods have been successfully developed for visualizing latent fingerprints, some of which are routine and others that are more specialized. Over the years, there have been many useful reviews of latent fingerprint recovery techniques, and current knowledge of chemical reaction mechanism and reaction conditions are typically included in these reviews, providing a good starting point for those interested in the science of latent fingerprint recovery. A latent fingerprint is formed when the sweat pores of the papillary ridges leave a deposit of perspiration on a surface with which the finger has been brought into contact. Human body possesses the following three types of gland, that is eccrine, apocrine and sebaceous, the secretion of which contribute to a fingerprint deposit. Eccrine glands are widely distributed throughout the body and are particularly numerous on the palms of hands and the soles of feet. These glands secrete chemicals as a result of general metabolism and catabolism. Besides water content, eccrine sweat contains up to 1% of the other substances with which inorganic salts constitute about one half. The other half is constituted by organic products like urea, creatinine, choline, lactic acid, sugars, uric acid, and amino acids. The amino acid content of sweat residue may be fixed by treating the fingerprint with a host of chemicals. The most commonly used is ninhydrin. However, where the latter fails to give prints of optimum quality, other derivatives such as 1,8-diisoflurane 9,1 or DFO may be called into action. In 1990, the chemical reagent 1,8-diaza 9-fluorinone, commonly known as DFO, became available as a more sensitive technique for fingerprint detection on paper. DFO reacts with amino acids in the latent finger mark in much the same manner as for ninhydrin. However, heat is required for successful development, and the reaction product is much paler in color than that achieved with ninhydrin. The advantage of DFO is that developed prints are highly luminescent at room temperature without any additional treatment. Studies have shown that up to three times the number of fingerprints can be developed with DFO in comparison with ninhydrin. DFO can be used before but not after ninhydrin processing. The disadvantage of DFO include the requirement for a specialized light source, the relative high cost of the reagent, and the unsuitability of the technique for luminescent substrates. A fingerprint developed with DFO is less visible in white light than after treatment with ninhydrin, but with green light, it fluoresces strongly. The fluorescence is viewed and photographed through orange or red filter. Now let us see DFO, the reagent. Amino acids constitute an important ingredient of human sweat. When a finger touches a surface, these analogues are deposited thereon as sweat residue. This deposition, called latent fingerprint, contains several other chemicals, such as inorganic ions and organic derivatives. However, Unlike other sweat constituents, amino acids neither interact with cellulose component of paper, cardboard, wood, and other porous surfaces, nor do they migrate within the capillaries of the substrate. As a result, reagents which give colored derivatives on interaction with amino acids render visibility to both fresh and old fingerprints on a wide array of surfaces. It is therefore not surprising that amino acid specific reagents have been used in several casework investigations. One such reagent is 1,8-diisoflurane 9,1, abbreviated as DFO. Original formulation of DFO involved 1,1,2-trichloro-trifluoroethane, more commonly known as Freon 113 or CFC 113. CFC 113 was the perfect solvent for the treatment of porous surfaces since it is non-flammable, non-toxic, and highly volatile, does not cause ink running, and produces stable solutions. Environmental concerns with CFCs and their detrimental effects on the ozone layer, however, resulted in the banning of CFC 113 in most industrialized countries under the Montreal Protocol signed in 1987. DFO reacts with amino acids in fingerprints, causing them to fluoresce. Use on porous surfaces such as paper, cardboard, raw wood, and sheet rock paper, not suitable for items that have been wet, must be used before ninhydrin silver nitrate and physical developer. The use of an alternate light source is required since this is a fluorescing process. Photograph prints to document can interfere with examinations of handwriting, body fluid trace evidence, and most other forensic examination. DFO is an amino acid sensitive reagent which develops latent fingerprints on porous surfaces like paper and wood. On reacting with the fingerprint residues, it gives a pale pinkish purple product. The reaction proceeds through the formation of intermediate yields and is similar to that between ninhydrin and the amino acid content of sweat deposition. However, while the reaction of amino acids with ninhydrin yields a non-fluorescent product, the corresponding reaction with DFO gives a luminescent derivative. The mechanism of reaction between DFO and amino acid residue leading the fluorescent product is depicted. The fluorescent nature of the amino acid DFO reaction product helps in developing weak chance prints that are often encountered at crime scenes. It also assists in detecting fingerprints on multicolored and glossy paper, shows one half of a representative sample fingerprint developed on paper with the aid of DFO reagent. The spectral characteristics of the fluorescence produced by DFO developed fingerprints have been investigated. It has been inferred that the fluorescent excitation wavelength occurred at about 470 nanometer, while the corresponding emission wavelength was centered at about 570 nanometer. When illuminated with green light, the developed fingerprints show strong fluorescence, which is viewed or photographed through an orange or red filter. The enhancement afforded due to fluorescence, some printing inks fluoresce under these conditions and therefore interfered with fingerprint detection. However, the optical brighteners present in paper do not hinder the visualization of prints. Fluorescent fingerprints visualized by DFO method normally reveal more details and clarity than those shown by ninhydrin developed imprints. Now let us see the methodology. The exhibit on which latent fingerprints need to be developed is dipped in the DFO solution. The solvent of choice for preparing the reagent is 1,1,2 trichloro trifluoroethane, abbreviated as CFC 113, but generally known by its common name, fluoresol. Lately, however, this compound has been banned due to its role in depletion of stratospheric ozone. Methanol, acetic acid, or petroleum ether serves as alternatives. A mixture of hydrofluoroether and trans 1,2-dichloroethene is almost as effective than CFC 113. The following procedure, subjected to minor variations, is normally adopted for developing latent fingerprints by the DFO reagent. The test solution is prepared by dissolving 0.5 gram DFO in 1 liter of the solvent in a reagent bottle. The surface bearing the latent fingerprint impression is immersed in the reagent for 5 seconds, dried, re-immersed for 5 seconds, and heated at 110 degrees Celsius for 10 minutes. The heating chamber is shown under white light. Pink purple ridges are rendered visible. The surface is illuminated with radiation of 470 nanometer wavelength, and fluorescence is observed through a 572 600 nanometer filter. The luminescence is at its maximum immediately after the heat treatment and then decreases slightly with time due to the absorption of ambient humidity. The luminescence may be restored to its original intensity by reheating the prints. Now let us see a comparison of DFO reagent with ninhydrin reagent. Both the DFO and a ninhydrin reagent are meant to detect latent fingerprints impinged on porous items like paper and cardboard and unpolished wood. It is therefore pertinent to weigh out the utility of one reagent vis-a-vis the other. The DFO technique offers the following advantages over the ninhydrin methodology. Number 1. With DFO, a strong room temperature luminescence of developed prints is observed without any secondary treatment. Against this, the ninhydrin developed prints have to be post-treated with a suitable metal salt to produce luminescence. Good results are obtained if the exhibit is cooled to minus 200 degrees Celsius during the fluorescence examination. With DFO reagent, results are obtained in a relatively short time of 30 minutes. Ninhydrin, on the other hand, develops fingerprint at room temperature in about 2 hours. For faster development, the surface in question has to be heated to about 80 degrees Celsius for improved results. Heating should be carried out in a humid atmosphere. Number 3, on an average, DFO reagent develops 3 times more fingerprints than ninhydrin. Number 4, if DFO reagent fails to detect a latent impression, ninhydrin method can still be tried out on the same surface. However, if ninhydrin reagent does not develop a particular imprint, DFO method cannot be extended for its detection. The DFO method has the following demerits as compared to the ninhydrin technique. Number 1, a high-powered light source with appropriate filter must be available for observing luminescence of DFO developed fingerprints. Otherwise, weak impressions will not be detected. Number 2, if the surface on which latent fingerprints are to be developed shows background fluorescence, the utility of the DFO method is curtailed. Number 3, DFO reagent does not give satisfactory results on heat sensitive items like thermal paper, window envelopes, and labels on polyethylene articles. Number 4, DFO reagent is costlier than anhydrine. Number 5, the working solution of DFO reagent is not very stable and tend to become cloudy. Now let us see sequencing of fingerprint detection techniques with other forensic procedures. Fingerprint detection should not be considered in isolation from other forms of forensic evidence. The effect of fingerprint treatment on other examinations must be taken into consideration with respect to document examination. Solvent-based reagents such as ninhydrin and DFO may cause ink running on treated documents and may destroy any intended impressions that may be present. A document examiner should be consulted before processing any documents that may require detailed document examination. Dear students, now let us summarize this chapter. So, in this chapter, we have learned that DFO reagent is a versatile chemical with broad spectrum applications for detecting latent fingerprints on porous items. Simultaneously, we have learned that, however, it is deemed less reliable as compared to ninhydrin reagent that works on analog articles. For example, it has been observed that at times additional prints may become visualized on an item if after treatment with DFO it is exposed to anhydrin. Then we have come to know that with DFO reagent, fingerprints are made visible in a relatively short time of 30 minutes. And we have learned that on an average DFO reagent develops 3 times more fingerprints than anhydrin. Original formulation of DFO involved 1,1,2 trichloroethane, more commonly known as Freon 113 or CFC 113. CFC 113 was the perfect solvent for the treatment of porous surfaces since it is non-flammable, non-toxic, and highly volatile. It does not cause ink running and produce stable solutions. Both the DFO and anhydrin reagents are meant to detect latent fingerprints impinged on porous items like papers and cardboard and unpolished wood. Lastly, we have learned that with DFO reagent, results are obtained in a relatively short time of 30 minutes. Ninhydrin, on the other hand, develops fingerprints at room temperature in about 2 hours.